Hello and good evening. Thank you for watching my PIC16F684 video series. You can find the playlist on my channel. Anyway, I'm jumping right into it, and I'm picking up where I left off from my last video. And I'm actually recording a screenshot of my last video, and watch that one first if you don't know what I'm talking about now. But I have this label here called bit tester, and effectively what it does is it goes through and tests each one of these bits. So I have 4 lines for the sake of testing bit 0, bit 1, bit 2, bit 3, and 4, and so on and so forth. But that seems a little bit amateur because I'm just copying out the same code. So is there a way to write some more efficient code? Can we optimize our code? You might know better than I do. I'm still an amateur. So that's what this video is about. It's an attempt to optimize this code here. So how do we do that? I like to be emphatic. So here is the sample code. I put it in a YouTube comment, and you can see the bit tester tests bit 0, bit 1, 2, 3, 4, 5, 6, and 7. And it's calling other subroutines. It calls a delay, and it calls the shift code routine, which basically clocks all of the 8 bits of data into the... what does it do? Oh yeah, this subroutine clocks each bit in after they're tested. And at the end of the testing of each bits, it has this L-clock bit, which latches in all of the 8 bits tested. But anyway, how can I optimize this to reduce all of these lines? Alright, well, I'm getting to covering my optimized code, but in that code I will be using an instruction that I am not as familiar with. Maybe you are, but I am not. Mnemonic operand, RRF. Rotate right F through carry. Machine cycles 1. Status affected, I guess it affects the carry bit. So I asked an internet friend to help explain this, just for interest's sake. I think I get it, but just in case. The RRF, rotate right through carry instruction, is used in PIC microcontroller assembly language to rotate the bits in a register 1 position to the right through the carry bit in the status register. Here's a detailed explanation of how it works. RRF, F, and D. F is the file register, the register whose bit you want to rotate. D specifies the destination of the result. So I take it for the file you could just use a hexadecimal numbered location. And maybe you could put, instead of a 0 or 1, you could put F or D, as is the common convention. Okay, I will read this. The RRF instruction performs the following steps. The carry bit is shifted into the most significant bit, MSB, of the register. Each bit of the register is shifted one position to the right. The least significant bit, LSB, of the register is shifted into the carry bit. But then again, the carry bit is shifted into the most significant bit, MSB, of the register. So I shouldn't think out loud while I'm recording, but it's almost as if the whole byte is shifted right into the carry, and then the carry bit wraps around and gets shifted into the most significant bit. Alright, so this builds on my code from my last video, so I won't recap everything. I'm just going to look at the changes that got made from the previous form of the code to this new optimization, this new optimized version of the code. Okay, I set up some equates for a delay counter, and I set up a RAM location for an arbitrary literal I want to store, and I want to run that through the shift register. But this is new. This is a new equate I called bit counter, and it's a counter for the sake of bit testing. I'm going to find out as I continue reading. I don't even know yet. Does 8, the number 8, get stored in here? Not sure yet. Okay, so it initializes port A pins. And then here's the constant number I wish to enter into the shift register. And it's the same number, 111-01010. And I move that number into the working register and then move it from the working register into that RAM location called C1 at 0x22. And then I clear F the bit counter. So now this bit counter definitely has the value 0 in it, or 8 bits that are all low. 1 byte that's equal to 0. Bit clear F, serial in. So I'm going to clear port A, bit 0, setting it low for the serial input, for the data input pin on the shift register. Next, I'm going to move F, the bit counter, which I know is 0, into the working register. Bit test file skip if clear C1. At this point, C1 is actually a memory location, and this number is now in it, and the least significant bit is going to be 0, and it's testing the least significant 0 bit. So bit test file skip if clear, so it is clear, so it'll skip it, and it won't set the serial in because it's going to skip over it. So the serial in effectively will be 0, and then it'll call the delay routine. It does it then it shifts the code. This, so far as I can tell, yeah, I left it the same as the previous code. It just clocks it in. And then it returns back here. And then here's the innovation. It rotates. I'll even add to the comments. Rotate right F through carry. And it does that to this name, which I gave to that memory location 0x22. So it takes this whole value, which is now stored in here, and it shifts the whole thing right. So instead of a 0 being here, there'll be a number 1 here. And it stores that shifted result in the file. Not the working register, but it stores it in the file. So everything is shifted to the right ones. INC-F, the bit counter. The bit counter was previously cleared, but now it's going to increment the bit counter 1 and store it in the file called bit counter. Bit counter is once again this memory location here. Next, it's going to move a literal value into the working register. It's going to move the decimal doesn't matter. It's going to move 8, the value 8, into the working register, and then it'll subtract the working register from the bit counter. Well, I don't know. If my math is correct, it takes 8, it takes the working register and subtracts it from the file bit counter. Now there's 1 in the file, so it takes the working register, which is 8, but it subtracts the working register from the file. So 1 minus 8. And then it's going to bit test the Z flag in the status register. The Z flag is the 0 bit. So when it's 0, when an addition or subtraction result is a 0, the status bit will be a 1. Z will equal 1. So bit test file skip if set. So it'll bit test the file. It shouldn't be set. Skip if set. No, it's not set, so it's not going to skip this line. So it will go to this line, and it'll go to bit tester, which brings it back up here. And it bit clears the serial input, which is hooked directly up to the serial input on the shift register. It just clears it. Then it moves bit counter into the working register. Just looking at this, I believe the bit counter is still 1, and it moves the bit counter, which is a value of 1, into the working register. Bit test file skip if clear. It's not clear. Well, it's the rotated bit, so maybe it's like the 1, which is now sitting in the 0 spot. So maybe it is set. So if it's set, it'll bit set F the serial input to match what the current bit is doing. Then it'll call the delay, and this shift code basically just clocks it in on the clock input on the shift register. And then shift C1 right by 1 bit. It'll rotate right F through carry, So now there's actually a 1 in this spot. So it'll rotate this into one position over to the right, and then it'll INC-F the counter. Now I think the counter is 2. Then it'll move a literal value into the working register. It moves 8 into the working register, and it'll subtract the working register from the bit counter, which is now 2, but it won't store it in the file. It'll store it into the working register. So it'll take the file, which is 2, and it'll subtract 8, which will give a wonky number that we probably don't even have to remember. It's just the point is that when it iterates and the bit counter gets up to a value of 8, it'll go, the bit counter will be 8, and then it'll subtract 8 from the bit counter, which will cause a 0, which will flag the Z status bit. So when it completely iterates through the code and does flag the Z bit, because it checked all the 8 bits in the byte, skip if set when this goes to a high, so it'll skip this line if it's set, so it won't break back into the bit tester and continue iterating. It'll skip this line after it checks all 8 bits, having rotated them to the right, and it'll basically just latch it all in with that L clock latch pin on the shift register. If that doesn't make any sense, you might have to study the pinouts on the shift register and experiment with the shift register to really understand that. But the L clock just latches all of the previously inputted 8 bits from the serial data in pin. The results of this subtraction operation probably don't really matter, other than for the fact that eventually the counter will be 8, and the working register will be 8, and the bit counter will be 8, and when 8 is subtracted from 8 and stored in the working register, that doesn't matter too much. When 8 is subtracted from 8, the status Z bit will be flagged and set. When it's set, it'll bit test file and skip if set, so then it'll skip this next line, breaking it out of the 8-bit bit tester, and then basically just clocking it in to the L clock latch pin. So this code does exactly the same as in my previous video. It just reduces the number of lines of code, makes it more efficient, and it's definitely harder to think through and understand. But I guess it's helpful because now, well, it's a little cut off. Not quite. 82, 83. 83 is the end directive, which is the last line of my code. So I have 83 lines of code. My previous example of code was 106 lines. So I reduced it by about 20 lines of code.